Dear colleagues, we are presenting a report on the topic of exact non-smooth penalty approach for a special class of linear programs. The co-authors of my report are Andreas Fischer and Olha Khomiak. Andreas represents Institute of Computational Mathematics of Dresden University of Technology. Olga and I represent Zhydkov Institute of Cybernetics. In our report, we will talk about non-smooth penalty approach and demonstrate its advantages on a special class of linear programs with big data. This topic is relevant, because gigabytes of RAM for modern personal computers require new approaches to development of methods for solving linear programming problems, LP for short. Our report consists of 3 parts. The first part gives formulation of linear programming problem and its application. The second part presents non-smooth penalty approach for linear programming problems, and the third part gives results of computational experiments that demonstrate the effectiveness of this approach. We will use scientific results of 2 scientists who worked at the Institute of Cybernetics. The first one is Norm's Uslavishore. We are going to use his algorithms to solve the non-smooth optimization problem that arises. The second scientist is Boris Mikhailovich. We are using his theorem on non-smooth penalty functions to establish penalty coefficient value for a non-smooth penalty function. Let us move on to the report. The first part is formulation of the problem and its application. It consists of 4 slides. The second and third parts are 4 slides as well. The first slide of the first part of the report presents a special linear programming problem. This classical problem in form of linear function maximization, optimal value of the objective function we denote as fmax, subject to inequality constraints and two-side constraints on variables. Lower bounds on variables set to 0, upper bounds get finite values, that is less than plus infinity. A feature of this problem is that the number of constraints is much greater than the number of variables. Let us assume that Ci is greater or equal to 0 and Bj is greater than 0. Condition Ci is greater or equal to 0 is not obligatory and can be omitted. But the condition Bj is greater than 0 is obligatory and it gives a possibility to set the penalty coefficient value. Using 3, for the value fmax it is easy to set the upper bound that equals sum of Ciui from I equals 1 to n. This upper bound we are going to use as penalty coefficient value for our problem. Such linear programs have numerous applications. This slide shows several tasks where they can be applied. I will mention only 2 of them, the robust linear optimization problem and the Boolean estimation problem. In robust linear optimization, constraint of the form A at Ix less or equal to B at Xi is considered, where the matrix A and vector B depend on a vector Xi that belongs to the uncertainty set U. If the set U is finite and contains hundreds of thousands or millions of elements, then we get a linear programming problem, where M is much greater than N. The second application is related to Boolean problem for graph independence number. This number is denoted as alpha at G. It corresponds to integer programming problem, which is given by relations 6, 8. I will not comment on this task in detail. It is a Boolean linear programming problem, and we will deal with relaxations of this problem. So, I am going to tell you about this problem in detail, which is connected to clique independence number of graph. Clique independence number is denoted as alpha q at G, where q stands for the clique, complete subgraph, in the graph G. The number alpha q at G corresponds to the 11, which is obtained with relaxation of the Boolean problem from the previous slide. In the problem the sum of xi from I equals 1 to n is maximized subject to two-side constraints on variables, constraints, 11, and clique constraints, 10, which can be numerous. Here the inequality sum of xi for I in V at Q is less or equal to 1 is connected to the fact that only one vertex from maximal clique can belong to independent set. It is clear that such problems can be extended by adding additional constraints to them, connected by odd cycles, p-wheels and cycles, p-wheels and other graph structures. Therefore, such evaluation problems fit to the special class of linear programming problems that we defined above. Let's move on to the second part, a non-smooth penalty approach. This is the central thing that we propose. It is connected to the linear programming problem, 1, 3, that we reformulate as linear programming problem in form, 12. Here the objective function remains the same, but right-hand side vector is equal to unit vector. The constraints are reformulated using some matrix H, which is defined with coefficients AJI, right-hand sides BI and upper bound vector UI. The central theorem in our report is the theorem 1 on non-smooth optimization problem, 13, 14. Here some penalty function fp at x is maximized with x is greater or equal to 0, where the penalty coefficient equals p. The function fp at x is piecewise linear concave function, so the problem, 13, 14, is a problem of piecewise linear concave function maximization. What do we get from the theorem 1? If the penalty coefficient p is chosen greater than f max, the optimal value of the objective function, then the linear programming problem, 12, from the previous slide is equivalent to the optimization problem, 13, 14. The problem equivalency should be understood as the fact that maxima set of the problem, 12, and maxima set of the non-smooth problem coincide. To prove the theorem 1, we used the theorem 2.14 from Boris Mikhailovich's book that I am going to tell about in the end of the report. To use Shinichny's theorem, we reformulate our maximization problem as a minimization problem, 15. This problem corresponds to the antisymmetric penalty function phi p at x being equal to minus fp at x from the previous slide. If the penalty coefficient p is chosen greater than f max, then the minima set of the function phi p at x coincide with the minima set of the problem, 15. The last, fourth slide of the second part is dedicated to the program LP-RALG, which uses our algorithm for solving the problem, 13. Non-smooth optimization problem from the theorem 1 is to maximize the function fp at x with x is greater or equal to 0, where the penalty coefficient is chosen being equal to the upper limit of the function f max. To take into account the non-negativity constraints xi is greater or equal to 0, we replace variables xi with variables modulus of zi. Then instead of the non-smooth function fp at x1, x2 etc., xn, we get a non-smooth function fp at modulus of z1, modulus of z2 etc., modulus of zn, all local minima of which are global. The aim of the LP-RALG program is to maximize the function fp at modulus of z1, modulus of z2 etc., modulus of zn. Now we move on to the third part of the report, where we demonstrate result of computational experiments with LP-RALG program. As test problems, the following linear programming problems were chosen. 1, 2, is our initial problem. Constraints, 3', are simplified constraints, 3, where the upper limit equals 1, that is the problem. 1, 3, is simplified. Coefficients of the objective function and constraint matrix are produced by using generator of random numbers uniformly distributed on the interval 0, 1. Right-hand side vector is calculated in such a way that the system, 1, 2, 3', has a feasible solution. solved in this case is the problem of maximization of the function fp at x with x is greater or equal to 0 and the penalty coefficient p equals sum of ci from I equals 1 to n, here ui equals 1, so they are omitted. The R algorithm parameters used for the computational experiments are as follows. Starting point is 0. Dilation coefficient alpha equals 4, step decreasing coefficient equals 1 or 0.99, starting step value equals 1. For computational experiments we used processor with 16 GB of RAM and rather decent by current standards computational speed. The programming language chosen is interpreter language GNU Octave 5.1.0. But it is not the best variant for fast calculations. On this slide you can see the results of work comparison of the program LPRALG and well-known package glpk work, for which octave function glpk was used. For not so big n equals 25, 50, 100 the number of constraints varies from 100,000 to 1 million. Solving times for this problem using the glpk package are presented in the third column of the table. They are increasing as n grows and maximal time of solving the problem with n equals 100 and m equals 1 million is 284 seconds, that is about 5 minutes. Time of solving the problem using the LPRALG program is 110 seconds, that is in 2.59 times faster than time of solving the problem using the glpk package. The worst acceleration equals 0.97, where the LPRALG program directly lost to glpk. In all other cases the LPRALG program won in 1.5 times average. Presented in the last column is norm of solution difference found with the glpk package and the LPRALG program. It is 10 power to -7, -8 or -9. It is worth noting that running time of LPRALG program can be improved as the octave language is interpretive. If the program is implemented using language that has tools for speeding up its work, then running time of the algorithm can be significantly reduced. This slide shows results of the second experiment, where M values were chosen such that the glpk package could not work. Here, data storage required 2.4 GB of RAM, if the matrix coefficients were stored in 8-byte words. The LPRALG program successfully solved these examples, though the solution times are not as good as in the previous example. They are about 5-6 minutes. The third and fourth columns show the results for step decreasing coefficients being equal to 0.99 and 1 respectively. When Q1 equals 0.99, more iterations and function calculations are spent, because of which the program runtimes have increased. For non-smooth functions, especially for maximum functions, the step decreasing coefficient is recommended to leave equal to 1. So, let's move on to the conclusions. The new solution method based on reformulation of linear program is an equivalent non-smooth optimization problem with non-negative variables is proposed. Its effectiveness is shown in comparison with the well-known glpk package for large randomly generated test problems with many more constraints than variables. In conclusion, I will give a list of used literature. The first two references concern applications of the considered class of problems. The first one is robust linear programming problems. The second one is estimates for the graph stability number. The third link is Boris Mikhailovich and Echny's book, where there is a theorem that we used to set the penalty value. The fourth link is Norms Yuslavich Shaw's book, where description of our algorithms is given. The fifth link is 2021 year work, where we have already applied a similar penalty approach to linear programs with many two-side constraints. Nevertheless, despite a general task was considered there, it was not possible to establish the penalty value in comparison with the special problem. The last link is the GLPK package, which is implemented in C and has a rather good computational speed. This package handles fairly decent problem sizes, including integer linear programming problems. The work was supported by 2 grants with numbers indicated on the slide. The first one is Volkswagen Foundation grant, which we are implementing together with the University of Dresden. The second one is a National Research Foundation of Ukraine grant. The report is over. Thank you for attention.